Okay, let's prove another rule for limits. So last time I proved a rule for sums, like if f of x goes to L1 and g of x goes to L2, then when I add them, when I do f of x plus g of x, I get that limit is L1 plus L2. This time I'm going to do a rule for products. So again, I'm assuming that f of x goes to L1, g of x goes to L2, but now what I'm proving is that the limit of the product of the two functions, the limit as x goes to a of f of x times g of x, is L1 times L2. So we are going to prove that in this video. Whoops, we're blurry. Okay, we're back. Similarly to last time, and maybe even more so this time, it's a good idea to do some scratch work. So I have started our scratch work here. Just like last time, I translated our assumptions. I'm assuming that the limit as x goes to a of f of x is L1, which means this, and the limit as x goes to a of g of x is L2, which means this. And what I need to prove is that the limit of f of x times g of x is L1 times L2, which means this. These are just the translations of my two assumptions and my desired conclusion. It's just translating those statements in terms of epsilons and deltas, because every limit statement is equivalent to another statement about epsilons and deltas. So let's take a look at the one that I need. Last time we did a trick with the triangle inequality. This time we're going to do something kind of similar, but I have to sneak in something first. This one part is a trick that comes with experience. This is other parts of this proof are probably more possible for you to learn and apply again. This one part is truly clever, maybe the type of thing that's hard to think of. I'm going to subtract something and then add something. So I'm going to sneak something here and here. I'm going to subtract and add the same number. So actually, I'm not really doing anything. I'm just adding and subtracting the same number. It's going to be a number that's carefully chosen so that, my plan is to group these two things together and then group these two things together. And the plan is to sneak it in a way that allows me to factor each part. So without saying too much more, let me just tell you what I'm going to sneak in. Why don't I do L1 g of x? That way I can factor this group because I can pull g of x out. I'll put L1 g of x there as well. And I'll be able to factor this group because I can factor L1 out. Okay? But this is something that I'm allowed to do. I just added and subtracted the same number, so I am allowed to do that. And I chose the number specifically so that it would share a common factor with this and so that it would share a common factor with this. So then I'm about to apply the triangle inequality to this part and this part. So I've got the absolute value f of x, g of x, minus L1 g of x. And then here I've got L1 g of x minus L1 L2. And like I said, I can factor each of those. Now, when I'm pulling something outside of an absolute value, like here I would factor out a g of x. Since it's in an absolute value, everything should be an absolute value. So it's absolute value of g of x times f of x minus L, which is also in absolute values. And then this one is like absolute value of L1 plus g of x minus L2. Whoops, times. Right? Oops, I'm being bad here. L1. Okay, I don't see any more mistakes for the time being. So where does this put us? I like the looks of this because f of x is going to L1. This is a number that I could, hopefully, when I'm writing a formal proof, this is the number that I could say is smaller than epsilon 1. That's here. I also like the looks of this. This is the number that I could say is less than epsilon 2. So I'm starting to like the way this looks. Now, what is still worrying me? Well, what's still worrying me is this and this. Because I know that I can say this number is less than epsilon 1 and this number is less than epsilon 2. I'm not, like, without thinking about it yet, I'm not sure what I can say about this number and what I can say about this number. So, that's what I need to work on next. I'm going to work on bounding these. And when I use the word bounding, I just mean, I would like to say that these numbers, for example, aren't too big, that they are no bigger than something that I come up with, so some bound on how big they can possibly be. The good news is that L1 is just some specific number. G of x, unfortunately, is not, but we can say this about g of x. So we can say that g of x minus L2 is less than epsilon 2. That would mean I can take the absolute values off and put this between negative epsilon 2 and epsilon 2. And then I can add L2 to everything. So this tells me basically how small g of x could be and how big g of x could be. So let me be careful about this, because this is g of x, and what I'm actually interested in is the absolute value of g of x. And this could be weird. I have to worry about negative numbers. For example, L2 could be a negative number. All of these epsilons and deltas, they're all positive numbers, but other numbers might be negative. And if I take a negative number and do its absolute value, that might be a large positive number. If I do a large negative number in the absolute value, that's a large positive number. What this means is if I draw a number line, like here's L2 minus epsilon, and here's L2 plus epsilon, right? Like it's this, g of x is in this open interval. So what can I say about the absolute value of g of x? I can say it's less than or it's the absolute value of g of x is less than whichever one's bigger between this absolute value and this absolute value. And I really don't know which one is bigger because I don't like L2 might be a negative number. So what am I saying? Since g of x is between these two numbers, the absolute value of g of x is at most the maximum of these absolute values. Okay, but let me say something better than that. I can use the triangle inequality on both of these, and actually, whichever one of these, whoops, forgot the 2 here. I can just write this. If I applied the triangle inequality to this one, I would get this, because the absolute value around epsilon 2, that just goes away, of the negative sign, I mean. Also, if I did the triangle inequality to this, I would just get this. So both of these are less than or equal to this. So g of x is less than or equal to this. In fact, let me say something even better, because I don't like that this depends on epsilon, or epsilon 2. And yeah, sorry, I'm very disorganized, but I just realized I forgot these 2's. So what I'm going to do and this is something that makes sense to do just about any time whenever you want. I'm going to go ahead and assume that epsilon 2 is less than or equal to 1. I could really put any positive number that I wanted here. For these epsilons and deltas, you're allowed to choose them as small as you want. They just have to be positive. So I'm allowed to assume that they're at most 1. I could say 1/100th or 1/1000th or 1/1,000,000th here if I wanted. I can just assume that epsilon is less than or equal to name whatever specific positive number you want, and I'm allowed to assume that. And then I just get to put a 1 here. I like that better. Okay, so where are we now? I might need more scratch paper. We were here, and I decided to start working on bounding these two numbers, g of x and L1. And we kind of decided that L1 was easy because that's just a specific number. And then we started trying to bound g of x, and we got, at least under this assumption that epsilon 2 is at most 1, we got that g of x is at most this. So let's go back to where we were. Under these assumptions, let me go back to this. Right, this. This was less than or equal to this. So let me rewrite that. This is less than or equal to, okay, what did we just figure out? I figured out that absolute value of g of x is less than or equal to this. So I'll put that here. That was absolute value of L2 plus 1. And let me actually also replace this with epsilon 1. Plus, whoops, this is L1. And I'm going to replace this with epsilon 2. And yeah, let me even say that this is less than or equal to, say, big M epsilon 1 plus big M epsilon 2, where M is just, let's see, I've got a number times epsilon 1 and another number times epsilon 2. By M, I just mean whichever one of these two numbers is biggest, like the max of absolute value L2 plus 1 and absolute value of L1. Because I just wanted to put the same number here and here. So it's M epsilon 1 and M epsilon 2. So, right. Ultimately, I want this to be smaller than epsilon. Of course, this inequality is not justified yet, but I get to choose epsilon 1 and epsilon 2. And actually, oops, let me... Yeah, okay, so sorry, this won't be any problem. If we choose, let's see, so I would want epsilon 1 plus epsilon 2 to be less than epsilon over m. If I make these epsilon over 3m, then I think this works. Because if I make them both epsilon over 3m, then when I add them up, I'm going to get 2 epsilon over 3m, and then I multiply this by m, and I get 2/3 epsilon, which is smaller than epsilon. So that's a good choice of epsilon 1 and epsilon 2. Right. Okay. So we have to put this all together. And actually, no, let me try to make this one video. I was tempted to cut it off and make a new video, but let's knock this out. Let epsilon be greater than 0. Now let's talk about epsilon 1 and epsilon 2. actually let epsilon 1 and epsilon 2 be the following. At some point I said epsilon over 3m, but I also said at some point, let's assume that epsilon 2 is at most 1. So here's how I'm going to say both things. I'm allowed to choose. What's important about these epsilons is that they be small. I'm going to choose them small enough to satisfy both requirements. In other words, I want epsilon 2 to be at most 1, so 1 is going to be in here. Also, I wanted these numbers to be at most epsilon over 3m, so I'm going to define them to be the min. And we're going to see that this works. So let me build my way up to this, because I basically have the proof written up in terms of scratch work. I just need to put these things in the right order. And I know that when I started just working on this directly, I kind of got stuck at some point because I needed to bound g of x. So maybe when I write the formal proof, that part should come first. So let me launch into that. So we know there exists delta 1 and delta 2 such that this implies this, and this implies this. Similarly to the last proof, I'm going to let delta be the min of delta 1 and delta 2. That way, if the absolute value of x minus a is between 0 and delta, then that means this is smaller than delta 1, and it means it's smaller than delta 2, because delta is just the min of delta 1 and delta 2. So like I said, we are launching into this part where we bound the absolute value of g of x, because when we were doing our scratch work, we knew that that was important. So for the values of x that we're interested in, for the ones from 0 to delta, we have, and now I'm kind of just copying this stuff from the scratch work. So I'm going to run through this again. We have, right, we have this. So so we've already done the algebra, so I'll go a little bit quick on the algebra. We have g of x is between L2 plus epsilon 2 and L2 minus epsilon 2. So the absolute value of g of x is less than whatever we wrote. The max of these two. And once again, we said that both of these were less than or equal to this, which is less than or equal to absolute value of L2 plus 1, because we already said that epsilon 2, epsilon 2 is less than or equal to 1, because epsilon 2 is the min of some things, including a 1. So I'm justified down here replacing epsilon 2 with 1. Okay? And so this is the bound on the absolute value of g of x that we wanted to establish. And okay, more paper. Okay, so we went through the work to bound g of x, and yeah, so let's go back to where? Now I'm at the part of the scratch work where I'm actually ready to do this, and I won't get stuck when I reach this point because I already have a bound on these. So I'm ready to go. Okay. So if you remember the trick, and I will do the algebra maybe a bit more quickly this time. This was f of x, g of x minus L1 g of x plus L1 g of x minus L1 L2. We use the triangle inequality on this part, and then I factored g out of this and L1 out of this. So I got this. Which is less than or equal to, right. Yeah, so, okay. Sorry, I have to stop here for just a second, because I'm ready to replace some things. Like I'm ready to replace this with the bound that we got, and this with epsilon 1, and then this with epsilon 2. But now I'm just thinking a little bit. I made a bad, or, well, I made something that needs to be fixed here. I never said what M was. Of course, we said what M was in the scratch work, but I never said what it was in the proof, so that's bad. I should have said what M was, where M is the max, and I'm just saying the same thing. I think I'm saying the same thing. Yeah. M is the max of absolute value L2 plus 1 and absolute value of L1. That's M. And actually, while I'm at it, M is a positive number, and that's important. In particular, it's important that M isn't 0, because I'm dividing by M here. I mean, that would be bad if M was 0. But M is not 0. M is a positive number. In particular, this is a positive number, right? Because if I take absolute value of L2, that's at least 0. And then if I add 1, that's definitely strictly positive. And since I'm taking the max of a positive number and this other number, technically this other number might be 0. It doesn't have to be positive. But because I'm doing the max would always be positive, because there's definitely one positive number in here. So m is a positive number. So yeah, maybe now I'm a bit more ready to go back to where we were. This is at most, let's see, what did we say? L2 plus 1. This is at most epsilon 1. In fact, actually, yeah, no, I'm fine. Plus L1 epsilon 2. And since we said m is the max of these two, so I can replace this one with m and this one with m. And again, we chose epsilon 1 and epsilon 2 to be whatever we chose them to be. Oh geez, where am I? Yeah, here we go. Each one of those is at most epsilon over 3m. So I can take epsilon 1 and replace it with epsilon over 3m. Epsilon over 2 and replace it with epsilon over 3m. M's cancel. I get epsilon over 3 plus epsilon over 3, which is 2/3 epsilon, which is strictly smaller than epsilon. So we got it. This is less than epsilon, at least under the assumption that, right, as long as x is close enough to a within delta, where delta is the min of these two. Okay, so we got it.